Now, number 6 was phrased in terms of results that you hopefully got when you released the ball down the ramp. But let's assume an acceleration of 1.2 domino lengths per cycle squared. Now, the mass of the ball is given to be 70 grams, and we're told that net force is equal to the product of mass and acceleration. So what's the net force in this case? Well, it's 70 grams multiplied by 1.2 domino lengths per cycle squared. And we multiply that up, we get 84 gram times domino lengths over cycle squared. Okay, now that's a perfectly valid unit of work and energy. Force. Okay, the unit can easily be converted to SI units, which we haven't really talked about yet because we want to understand units rather than thinking of units as something handed down to us on a stone tablet. So, grams can convert to kilograms very easily. Replace gram here by 0.001 kilogram and you have started a conversion. Domino length is 5 centimeters, we know that. That's 0.05 meters, so we can put 0.05 meters here. And cycle, well, I don't know how long your pendulum was. I don't know what your cycle was. Maybe the cycle was 0.8 seconds. Okay, so the time of a cycle might be 0.8 seconds. And we would then be able to express this in units of kilograms times meters over seconds squared. And I'm going to actually go ahead and write that out and pin that to the video here. Now you can work through the numbers more precisely. Just giving you a ballpark figure here. Replacing the gram by 0.001 kilograms, domino length by 0.05 meters, and a cycle by 0.8 seconds. We work out the numbers down here. We're going to get kilograms times meters over seconds squared from the units. The numbers are going to be what they are. And when you multiply them by 84, you get about 0.006 kilogram meters over seconds squared. Turns out that is an SI unit of force. That is what we call a Newton. So this would be 6/1000ths of a Newton, accelerating the 70-gram ball at the rate that you observed. Now we calculate the work done by the force F net. And you're told in problem 7 that the work is a product of the force and the displacement in the direction of the force, the component of the displacement in the direction of the force, or alternatively, the component of the force in the direction of the displacement multiplied by the displacement. Okay, and we'll sort that out when we work a little bit more with the vectors involved. For most of the applications we're going to use in the immediate future, the force, net force, and the displacement are going to be in the same direction, or at least along the same line. So they'll either be in the same direction both, or in diametrically opposite directions. Okay, now F net is, as we found here, 84 gram domino lengths per cycle squared. And of course you want to calculate it for your data as well. And we multiply that then by the delta S, which is 12 domino lengths. And we get, if I multiplied it correctly, which is questionable, 1008, because 84 times 10 is 800, and it's 840, and 84 times 2 is 168, and you add those up, you get 1008. Or 12 times 80 is 960, 12 times 4 is 48, 916, 48, I think I got it right. Okay, anyhow, that multiplies out to 1008 what? Grams times domino lengths squared divided by cycle squared. Now we could do the same thing we did down here, same substitutions, and get this in SI units. It would come out in kilograms times meters squared per second squared. And that would be what we call a joule. I'm not going to write that one out, but it would be easy to do. Okay? So that's our result for problem number 7. So we've introduced the idea of net force through Newton's second law, and we've introduced the idea of work, something that we don't usually do in a physics course, but I kind of do. because they're closely related, and they're closely related to what we're going to look at here in a second. Now, I've skipped number 8, where I ask you to compare this with the change in 1/2 mv squared. Okay, mass is 70 grams. Your velocity will be in nominal lengths per cycle, and you'll be able to calculate 1/2 mv squared at the beginning, 1/2 mv squared at the end of the ramp, and subtract them and see what that result comes out. And you really need to do that. Don't think you'll have a whole lot of trouble doing it. Now we're going to move on to number 9, and numbers 9 and 10 introduce two additional ideas that are going to be very important to us.